It's an analogy, okay, to get some insight into how to do this. So I say, here's an object, I apply a force, and I ask you the question, what is the acceleration of the object when I apply a force F? So how would you do it? Okay, 8th or 9th or 10th grader can do this. They would ask me, what's the mass of the object? Okay, I ask you, what is the acceleration? You turn around and ask me, what is the mass of the object? I tell you the mass of the object is m. And then you say, sure, A is F divided by m. Done. It's as simple as that. Okay, I could have gone into all kinds of differential equations and so on to figure that out, but you asked me for the mass, and you gave me the answer, A is F divided by m. So you ignored a bunch of things. You ignored the shape of the object. You ignored its color. You ignored its temperature. Okay, and you ignored the soft or hard or whatever. Okay, you ignored a whole bunch of things. You're focused on one thing. Okay, you're focused on its mass. And it turns out that that process really was developed from a set of simplifications that is called, does anybody remember this? Point mass simplification. Okay, so in physics, you've done this before. Okay, you've simplified your lives by viewing objects as objects as having a mass at a point and forces acting at that point. Okay, m is that property of the object that is of interest to you. This process is called, in physics, point mass discretization. Okay? Now, use that analogy, and I'm going to show you a similar simple process to do the problem with the light bulb. Okay. So take my light bulb again. And I focus on the filament of the light bulb. Okay? All I care about is the current flowing through the light bulb. Okay? I don't care about whether these wires, whether the filament is twisted, whether it's hot. I don't care about its shape. I don't care about its color. All I care about is the current. Okay? So to do that, what we can do here at a very high level is, since we just need the current and don't care about a bunch of other properties, we will simply replace the bulb with the discrete object called a resistor. Okay? So the discrete object is a resistor, much like the point mass simplification that we did earlier. Replace the bulb filament with a object called a resistor, the discrete object called a resistor, or a lumped object called a resistor, and put a value next to it, just like the mass for the object, a resistance value, R. Okay, now what I can do is, in the same manner, replace the battery with an object called a battery object, and connect that here. The voltage V applied to it. V falls across the resistor. And I get my I simply as, from Ohm's law, as V divided by R. Okay? So notice here, we replace this complicated bulb, this really twisty, weirdo thing, with this discrete thing called a resistor. And its only property of interest was its resistance value R. Direct analogy to what we did there. So since R represents the only property of interest, we can simply ignore all the other things. So you notice here, we've done things the simple way. Okay? And remember, in EE, in electrical engineering, we do things the simple way. Okay? We could go the hard route and do Maxwell's equations. Okay? And get PhDs in physics and so on. But out here, we're looking to do useful, interesting systems in the simplest way that we can. Okay? We do things the simple way. All right? So we just did this, and boom, I found out what the current was. Now, I've cheated a little bit. R is a lumped abstraction for the bulb. So when you look at this resistor here, that is simply a placeholder. It's a stand-in for this complicated thing called a bulb. It's a discrete object. It's a lumped object and represents the bulb. Now, so most of 6002 will take off from here. Okay, and that's it. To very simple stuff like V is equal to IR. It's just simple high school algebra. We'll take off in that direction. But before we go there, it's important to understand why was it that we were able to make this simplification. Okay, we did something else here. Something's going on under the covers here. Okay, on the one hand, I say, let's use Maxwell's, and then I jump about and say, hey, we can just use a simple thing. I did something that allowed me to go from here to here. Okay, and you need to understand why I did that and how I did that. Understand it once, and then you won't have to need that information again. You just need to understand it. So let's take a closer look at the bulk filament and look at what we really did. So here's my filament, A, and let's say that the surface area here, I labeled that SA, and the one down here as B. My voltage V applied there, and this is what I call my black box that I replaced with a resistor. Notice that in order for this to work, V and I need to be defined. So I needs to be defined, and V needs to be defined. Okay, if I give you a random object, and I don't tell you anything else about the object, it's not clear I can do that. Okay, if it's a much more general situation, I have to write down Maxwell's equations, and this is what I would write down. Write down J dot D as a current, as a function of the coordinate here, integrated over the area, minus okay, I would have to start from there. Okay, from one of Maxwell's equations. All right? Notice that this becomes IA, and this becomes IB in our simplification. But if I don't tell you anything else, you have to start from here. You might have some kind of varying current here by point. You might have some other current coming out here, because I may have some charge buildup happening inside. If charge was building up inside the filament, then I would have to put del Q by del T out here, right? The current in minus the current out must equal charge buildup. Whoa. Where's this and where's that? So this is reality. This is really what I have to do. Okay? But how did I get there? How did I get there? The key answer is, as engineers, when in doubt, we simplify. Remember, we're engineers. Our goal in life is to build interesting systems. Okay, and some may also be motivated by money. Okay, so our goal is to build interesting systems and do good to humanity. Right, so as long as we can build a good light bulb, we're happy. So what we can do is we can say, look, all I care about is building interesting systems. So what I can say, hey, this stuff is too hard. Let's make the assumption that all the systems that we will consider will have this thing be 0.